Real pleasure to be in Sydney for a few weeks and to be here for part of this. I lead the NASA Quail group, and there are about 15 of us who work full-time on theory and numerics. People often ask me why NASA does quantum computing, so I just thought I would mention that our mandate is to determine the potential for quantum computing to enable more ambitious and safer NASA missions going into the future, and to also help realize that dream. And while we're not in the top 5 or 10 at the moment, NASA has long had a large supercomputing operation, and the quantum computing groups is sort of modeled on that. As if there's time, I'll get to right at the end. So we do everything from working very closely with the hardware folks and doing co-design between hardware and algorithms and protocols, solvers and simulators, particularly in physics-inspired classical solvers. I'll just mention that I like to say that there's one area of quantum computing that seems to be underhyped, and that strangely, that's the one area of quantum computing that is useful today, and that is quantum-inspired classical algorithms. And this is partly to try to change the mindset of people. I think most people in the field view it as a failure when somebody dequantizes a quantum algorithm. I think we should take it as a big success for the quantum viewpoint. So we enjoy doing that sort of things, and some simulations, software tools, compilation, parameter setting, et cetera, up through algorithms and application areas, and some quantum networking and quantum distributed computing. I have two overview articles listed. We have written a newer overview article which should be out within the next few weeks. And I just want to I'll point to him again, but Namit is also here from the group. So that's a brief overview of what we do. I'm now going to do something very odd, I guess, which is that I figured that this was a time to discuss things, and I really wanted to be able to discuss at least 2 very different topics. So I'm going to rush through 2 topics, thinking that we have the rest of the week to talk about these things. So I hope that will be simulating. I know at least one person was grateful that half of it didn't seem to have much to do with error correction. So. The other half does, but anyway. So I'm going to start with some work on Wigner's Friend that was done with Howard Wiseman and Eric Cavalcanti up at Griffith University. And how many of you know about the Wigner Friend scenario? Okay, not too bad. How many know Schrödinger's cat scenario? Yeah, pretty much everybody. I actually don't know why the Schrödinger cat is so much more popular, where you can go buy mugs and things like that, whereas Wigner Friend is not as well known, even though it also pushes on questions of measurement, observation, reversibility, et cetera. And I think it deserves to be better known. So it comes from some remarks that Wigner made in this 1961 paper. And I'm just going to read it. So he says, it's natural to ask about the situation if one does not make an observation oneself, but lets someone else carry it out. What is the wave function if my friend looks at the quantum object? So what's my wave function if somebody else looks at the quantum object? And the answer is that one can only attribute a wave function to the joint system of the friend plus object, which follows from the linearity of the Schrödinger equation. But this appears absurd because it implies that my friend, in his words, was in a state of suspended animation before he answered my question. And so this is a very foundational sort of question, but one of the exciting things is to try to turn foundational discussions into something that's more empirically testable. So that's actually where believe it or not, that's where we're going with this. So people have more formalized Wigner friend scenarios since then. So for example, a friend performs a experiment. What is the state for Wigner? Now suppose Wigner had superpowers. In principle, everything's reversible in quantum mechanics, right? So in principle, Wigner could reverse everything that happened in his friend's lab, including his friend. And he then has a choice. He could either ask his friend what his friend observed, or he could reverse everything and make the measurements himself. And you can start looking at probability distributions related to those outcomes. And it's more interesting if you extend this in a way that it's tied to Bell-type inequalities, where you have experimental with superpowers with a friend and another experimental with superpowers, and they share an entangled state, and then you can get some very interesting inequalities. So that's the general setup, and I'll go through some of this. I'll revisit this slide later, but I just wanted to point out that where we're going is that there are a number of different versions of this, but in a 3-setting 2-outcome case, we can get a complex polytope. It's an interesting geometric object in and of itself. And it's possible to have quantum states that violate the inequalities that come out of these Wigner friend scenarios. The inequalities we're calling local friendliness for reasons that will become clearer, that violate these local friendliness equalities, that's strictly weaker than the assumptions are strictly weaker than those for Bell's inequalities. And that's interesting from a foundational point of view, because it means that you can't as easily get out of things. Not that it's easy in Bell's theorem either, but there's some outs in terms of what assumptions you can give up in Bell's theorems that you can't do to resolve the Wigner friend. So we'll get to that in a little bit. So, but where I want to go with this is, well, what if we could actually do this experiment? Okay, so that seems kind of crazy, right? Do we really believe somebody could ever have superpowers that could reverse a human being in a lab, et cetera, et cetera? And maybe not, maybe, I don't know, it's very hard to say in the longer term, but maybe we can do something pretty interesting, which is, what if we instantiate our friend as an artificial intelligence, preferably a human-level artificial intelligence running on a quantum computer, okay? And then quantum computers are reversible, so we can have our artificial intelligence QALY. Anyone know where QALY came from? Yeah, Wally and Dolly, and yep. Anyway, we had fun. QALY can be reversed. QALY is just running on a quantum computer, and so we're gonna talk about how this works out. And my role in this mainly was that Howard reached out to me and said, you know about quantum computers, do the resource estimate for this. And because he hasn't done resource estimates for quantum computers and other things, I think both he and Eric Cavalcanti were very dismayed by the large resource estimates. But they were, not to give too much away, I mean, I'll give you the insane numbers later, but they're not very far off from like Will Zhang's and co-authors' estimates for portfolio optimization advantage. So, I mean, you know, it's, and we're basically going to do a very loose upper bound. So, and where I want to go with this is I'm going to give those resource estimates. There's a single photon experiment that's been done, And I think one thing that would be really interesting to discuss with people here is what are compelling intermediate experiments that will really propel the program along. So just to go into this in a little more detail, so Alice is communicating with Quali, and Alice will randomly choose whether she just accepts Quali's message, or or between two options where she'll reverse and measure herself, but in two different bases. Okay, so in order for her to measure herself, so the way Quali is communicating is Quali measures and then sends a message. And then Alice either reads the message or sends the message back so that everything can be reversed. And so returns the message. The whole computation is undone, so the system being measured is now unentangled with Quali, and Alice can now make the measurement herself. And we can look at inequalities arising from this situation, and that's what I was showing in the polytope early on. So let's look at this a little bit more. And I want to talk a little bit more about the reversibility requirements. So the reversibility is only needed for length of time to carry out the experiment. So you can sort of do this in pieces. We estimated that it would take a human to interact with the qubit, think about the result, compose a message, and send it off to Alice roughly a second. If you we can do estimates for other, but order of magnitude a second. And so we wanted to understand what it would take for AI to do this. Well, we don't have a human level AI. So what we needed to do was look at what are the estimates that people have for human level AI. And I want to make an important point that we need to only reverse at the logical level. We don't need to reverse at the physical level throughout this. So sorry to the person who didn't want any error correction. So there's a little bit of error correction in here, but I won't be talking about specific codes or things like that. Okay, so we'll be reversing at the logical level. I mean, some people also asked, can you really do this even in a measurement-based quantum computing? Absolutely, because we're reversing at the logical level. We're not looking at the reversing at the physical level. So let's see. So we're going to segment the AI algorithm into pieces where we're looking at that AI algorithm and all of the gates that are done within 1 second of that AI algorithm, that unknown human level AI algorithm. And we really would like the algorithm to run at roughly human speeds. If it takes years for quote human level intelligence to return an answer, maybe that's not really human level intelligence, but this turns out to be very, very challenging. So we segment into these 1 seconds. We look at the resources that are required classically to do that. And then we go through and look at what does it take to implement those on a quantum computer. So where do we get the classical estimates from? This was pretty hilarious, some of it. So there are a bunch of published estimates for the number of bits and the number of flops that you would need to have a human level. And there are a few survey papers. And I think my favorite number in all of these is that one estimate says that you need 10 to the 8,432 physical bits for this, which is beyond the Bekenstein bound. So it's probably unphysical. So when we were looking sort of at what would be good estimates, we sort of threw that one out. But it was amusing to see. So the highest reasonable estimate, other than that one, and that one's probably not reasonable, was about 10 to the 28 bits, and most of the estimates were within a couple order of magnitude of 10 to the 15, so we took that. And similarly for the published estimates for flops were from like 10 to the 12 to 10 to the 28. And again, 10 to the 15 seemed like a pretty good spot. One thing to recognize is that it's only very recently that you could do this on a supercomputer. I think it's only within the past 5 years. So it's pretty challenging if these estimates are right. Who knows? So as many of you know, there's logarithmic overhead in translating from a classical algorithm to a reversible classical algorithm. And once you've done that, you can translate directly to a quantum algorithm. But then you want to look at how large the device is and what the architecture is in terms of routing, what gates are native, et cetera, et cetera. We made an architecture assumption where we considered architectures with a certain number of chips with 1 logical data qubit and 2 logical ancilla so that you could do a Toffoli gate. People are like, you're crazy. Why do you only have 3 qubits per chip? That's crazy. But if you look at a lot of the error correction estimates, that's not so crazy. In fact, I asked a panel of people a couple years ago at QCE how many logical qubits they thought would be on a chip. Everybody except one person from Google refused to answer the question, and he said 4. So this isn't, and I think the most common answer I've heard of people who've really thought about it is something like 10. But you know, anyway, we have all these chips, and they can hold, you can do a Toffoli gate on them, and they're connected by a 3 regular graph. They're beautiful cyclic butterfly graphs, but there are other possibilities here. So those are the assumptions we used. You can use other assumptions. We actually have a spreadsheet for certain assumptions. Using all these assumptions, we got a loose upper bound where what had been what took place in 1 second is now taking place in 600 years. So we need to improve this a bit. There are a bunch of ways that this might happen. I think we're all hoping for hardware advances with lower error rates, faster measurements, faster gates. Maybe the HLAI requires fewer resources. We asked ChatGPT. ChatGPT gave us a higher estimate, but was unable to provide any argument or references. Now, this was ChatGPT-3. I don't know, I haven't asked ChatGPT-4, but anyway. Also, we're just taking a generic algorithm, almost certainly something with some structure. You'd be able to reduce the overheads. Perhaps this algorithm, which is essentially classical, except you have to run it in superposition on a quantum input, has inherent robustness. Eric's particularly excited about the possibility of a efficient native quantum human-level AI. This is kind of amusing that the reason you're doing quantum computing here and having it be native quantum is not because you think there are quantum effects going on in the brain, but rather you're trying to catch up with the speed of classical brain processing. You can do more sophisticated use of structure. There may be quantum subroutines. You may not need to reverse everything. Yeah, lots of possibilities here. So I'm fairly optimistic that we can cut down quite a few orders of magnitude, but it's still probably going to be a while. But even before you can do the experiments, if you think that human-level artificial intelligence can be physically implemented, and that a universal quantum computer that could run such a thing is physically possible, then you already should be trying to struggle with the fact that the four metaphysical assumptions are not compatible with assuming that if you do this, you get what quantum mechanics predicts, which is a violation of certain inequalities. If that turns out, you're going to have to reject one of the metaphysical assumptions above. Howard and Eric have a nice, they're much more up on interpretations of quantum mechanics than I am, and they have a nice chart talking about who gives up each one of these. But the one thing we do know is that if the predictions of quantum mechanics hold, then, and these are possible, then you have to give up at least one of these. And it's probably even more exciting if the predictions of quantum mechanics don't hold. I think one really exciting thing, I think many of us are first interested or really caught by sort of foundational issues in quantum mechanics and its surprise. And then some of the work as people think about that is not very grounded, and it's really exciting to see when you can turn some foundational issue into some experimental setup with Bell having pioneered in this direction. So as I mentioned earlier on, there has been a proof of principle experiment where the violations were shown with a single photon acting as a friend. For those of you maybe in optics who think that your photons have as rich experiences as human beings, you may be perfectly happy with this experiment. But some of us aren't quite that friendly to single photons, and so we would like to see something a bit more. So what are interesting things that you could do between a single photon experiment and this large-scale human-level artificial intelligence running on a quantum computer? That's open for discussions. Some of the things we've thought about are successively more complex friends, things that look computationally hard to reverse, so they're ties with quantum scrambling, quantum chaos, operator entanglement. There are other notions of complexity, maybe quantum computer simulations of physical measuring devices, quantum simulation of simpler biological organisms. For example, the C. elegans connectome has been mapped. One issue is that other than for the C. elegans, we don't really have a compelling threshold. Like, if you want to do more complex friends, what's a really interesting level of complexity? And so I think there's some real theory to be done here as to what for example, has certain agency properties or something like that. So anyway, I just wanted to throw this out for everybody because I think there's the Bell's experiments have been more or less completed with loopholes closed, but there's lots of opportunities here for some possibilities. And I'll just mention that there may or may not be ties with being able to do quantum advantage. I briefly alluded to this earlier. So there's questions as to how best to verify quantum hardware and quantumness in hardware. Our group was a small piece of the Google quantum supremacy experiment that got a lot of publicity, and also more recent updated one last year. And one of the criticisms that people have had is that, well, you can't really verify this. Well, if you can't simulate it, how can you verify it? So the approach people took was verify it up to the point you can't simulate it anymore. Take your circuits and replace all your 2-qubit gates by Clifford gates, and then you can simulate and make sure that works, and a bunch of things like this. And then it seems unlikely that just at the point where you just can't simulate at the moment, there's suddenly something crazy that happens. But it would be nice to be able to verify it more directly. And there's some other possibilities. For example, most people would be pretty convinced by a factoring of cryptographic scale number. Either you've succeeded in implementing Shor's algorithm or you've done something even more surprising. But we're a ways away from that. So one possibility is that people have looked at non-local games, which you heard about this morning, and replacing the non-locality with encryption, and then you can do verification. And this is very deep connections, not only with things in quantum complexity, like the big MIP star equals RE, or the Searlson's bounds on the violations of entanglement, but also to deep conjectures in operator algebras like the Kunz embedding conjecture. Anyway, maybe there's a Wigner friend game that could provide an interesting verification protocol. That's another direction to go. So that's all I was going to say on the first topic. So maybe I'll pause here for any clarification questions. I think I won't take speculation questions yet. Any clarification questions? Okay. Wow.
So
yeah.
I think I resolved this question in my head, but just in case anyone, you want to have a quantum version of a human scale AI so that it's really a friend.
Right.
I mean, at some point I was like, well, why does it have to be so big? But you want this thing to be able to achieve other tasks.
Yeah.
Stimulate a friend.
Yeah, exactly. So there's probably there's probably even a long pre-experiment phase where you're interacting with the human level AI and deciding that, yeah, they qualify as a friend. They have maybe I should have at least read the friendliness one, is that if a system displays independent cognitive ability, at least on par with my own, then they are a party with cognition, at least on par with my own, and any thought they communicate is as real as any thought of my own. And generally, there'd be some way of interacting with them to determine that their cognition was on a par. Yeah, I think there are different ways of looking at this, and some people wouldn't. I think requiring a cognitive ability that high may be more than we need. A lot of people think their dogs are way more friendly than their, anyway. Yes?
How do you quantify some of this mathematically?
Yeah, so you can actually turn a lot of this into space-time diagrams and probabilities on the measurements and what it implies about the probabilities. So we can. I mean, it's not trivial. Where's the? I mean, Bell's inequality is one inequality. Here we get a whole bunch of different inequalities, and these aren't even all of them because you have to do symmetrizing of all of these, and it, as I said, the polytope gets. But yeah, we can walk through some of that. But yeah, it's not trivial. Yeah. Cool. Any other questions before I switch gears entirely? Okay, so just a couple weeks ago, we posted this paper on the arXiv. We were looking at these dynamical codes, and the motivation is really that, as I'll say in more detail later, there were certain dynamical codes known, and it's still, I think, very unclear how general the construction is and what goes into that. And so we were just playing around with it, and we have a different set of Floquet codes. I'm not trying to make a claim that these are important for some practical error correction experiment at the moment, but I do think it's important for us to understand how to design these things and what the design space is. And while this doesn't understand this doesn't answer that question fully, it gives us at least another piece of the puzzle. So that's where I'm going with this. We're going to build them on top of Bacon-Shore subsystem codes. I want to thank the speakers this morning who did a wonderful job of setting things up for multiple things in my talk. So I'll just briefly review the Bacon-Shore subsystem codes. So you have a gauge group generated by all nearest two-body actions, two-body operators of the following forms. You have XX checks, which unfortunately I think I used exactly the opposite color scheme from this morning. And I still sometimes get confused. So I apologize if I sometimes say horizontal versus vertical or something like that. But anyway, we have XX checks between all pairs of horizontal qubits, nearest neighbor qubits, and ZZ checks between all the blue vertical ones. And the stabilizer subgroup is the center of that gauge group. So it's elements that commute with all elements of, sorry, that should be elements of G, S that commute with all elements of G. Sorry about that. So one stabilizer generating set for this is columns of XX operators. If you do a little math, you'll see that commutes, and similarly rows of ZZ operators will be your stabilizers there, okay? So most of the time we just look at, okay, what's a logical qubit? So that should be something that's in the normalizer, but not in the stabilizer group, and so we can check that we can define the vertical operator here as our X operator and the horizontal operator here as our Z operator and get a logical qubit out of this. But there are other things that will be helpful as we go forward to think about this in terms of some virtual qubits. So for each plaquette, each of these square plaquettes, we can define some operators that correspond to products of X operators in a partial column and products of Z operators in a partial row extending out from the plaquette. And that's one-to-one correspondence. We also have stabilizers. So we saw the stabilizers earlier. And then to complete those as stabilizer qubits, we need to take our Z operator and we need to find X operator that anti-commutes with it. And one nice thing is that we can think of these as horizontal stabilizer qubits and logical qubits as just extensions of our gauge qubits in the sense that you can put a virtual plaquette off the side and then it's just the operators that you would, that's sort of defined by that virtual plaquette. So the Z operators to the right and the X operators above. And that's even true for the logical operator. So hopefully that helps you to visualize these things a little bit. I'll just mention that one thing you can think of is just the 412 case. It's a error detecting code, but being able to do something with just 4 qubits can be super helpful. And so you have your gauge operators, you get your stabilizers. The stabilizers would define a 422 stabilizer code, but because this is a subsystem code, what we end up doing is we are able to do lower weight measurements just using the gauges, not the stabilizers, but we only get one logical qubit here, so there's a trade-off. And I'll just say as a side note, we used this a number of years ago to get around a no-go theorem for stabilizer codes in terms of error suppression in the adiabatic setting, which was a fun project. So anyway, I realized I should have said one other thing on the Bacon-Shor codes, which is you can also define generalized Bacon-Shor codes where you don't have a rectangular lattice, but you have other geometries, other carved out rectangular geometries. So let's see here. In the Bacon-Shor code, you can think of this, and this is sort of going to lead into the Floquet codes. You can think of this as having 2 rounds of measurements. You're measuring all your XX checks, which commute with each other, and then you're measuring all your ZZ checks. Again, they all commute with each other. But round 1 and round 2, you have operators that don't commute. If you put them together, they don't commute with each other, okay? So we are periodically moving between 2 different gauge fixings, one where the X operators of all the gauge qubits have been fixed, and the other where you're fixing the Z operators, okay? And you can think of this as having instantaneous stabilizers groups that change from round to round. So in one round, you get all of the Bacon-Shor stabilizers, plus you've fixed all the things you've just measured, so all the X gauge qubit operators. And then at the next stage, you still have your stabilizers, but you've now fixed all your Z checks because that's what you've just measured. And so that can help you think about, that will help you think about the things I'm going to say going forward. So I'm just going to very briefly touch on the honeycomb code because that's what people have seen, and then go on to what we did. So in the honeycomb code, we have these hexagonal plaquettes, and on the horizontal rungs of this hexagonal lattice, there are ZZ checks. On the sideways oriented this way, it's YY. On the sideways oriented this other way, it's XX. And you'll note they don't all commute with each other, right? And what they suggest doing is to measure these in 3 different rounds. So in the 0th round, we will measure everything on the 0 plaquette. So the X, Y, and Z operators on the 0 plaquettes. And then at the next round on the 1, and then on the 2. And if you measured everything all at once, you'd just get a mess and no logical qubits. But by doing this round by round, at each round, you have an instantaneous stabilizer group where you have some logical qubits. And then at the next round, you're going to have preserved that operation as you go into the next round because you have multiple operator representations of the logical qubits, and you can do that. You can use those to preserve the logical structure from time to time, and it's periodic. That's why it's called Floquet. There's some discussion as to whether there could be some interesting non-periodic ones. I won't go there. And there was a general construction related to this for 3-valent, 3-colorable graphs. But a lot of people were asking, how generally can you do these constructions for the Floquet codes? And we were just trying to understand what's going on, and so we decided to look more carefully at what was going on with the Bacon-Shor codes. So in order to get an additional logical qubit, what we want to do is refrain from fixing some degree of freedom. And so we introduce a gauge defect, and we need to do things carefully to ensure that all the stabilizers do get measured. So what we do in our first code is we find a block of 4 square plaquettes, and it will be advantageous to put these in the middle for reasons that will become clearer later. And in the first set measurement schedule, we measure all of the XX checks except for the ones above and below 2 of those plaquettes in a left column. So we're still measuring the one in the middle here, but we're not measuring any of these, okay? And then we do that for the ZZ checks, and then we move over a column. So you'll see that this is similar to that, but we've now moved over a column. And then we move down a row here, and then we repeat this structure. Okay? So what does that end up looking like? So we want to look at what the instantaneous stabilizer group looks like here. So at any round, the instantaneous stabilizer group consists of the usual Bacon-Shor stabilizers and the just measured check operators, and all elements from previous instantaneous stabilizer group that commute with the currently measured checks. And if you do the math out, what you find is that you have your Bacon-Shor stabilizers, plus you have remember how we were defining those gauge qubits, and basically you have, you're fixing these gauge operators aligned with the particular plaquettes you've called out. So we've colored things that are fixed. And you'll notice that in the Bacon-Shor code, this would have all been red because you would have fixed all of you would have measured all of and therefore fixed all of the check operators. But in this case, we didn't measure these. And so we have some of these operators that carry over from the previous round that are Z-type operators as opposed to X-type operators. So that gives you some feel, I hope, for what we did. We then can look at what happens for the entire measurement schedule. So we have similar diagrams to what I just showed. And then I've written what the logical operators are here, and these are the logical operators that were on that previous slide corresponding to the plaquettes. And you'll notice that as we go from here to here, we had XA, and now we have XA times XB. Well, XB is in the instantaneous stabilizer here, and so that's a legitimate thing to multiply by. And we're going from ZD to ZB, and at first that looks a little bit scary, but you'll notice that we've set things up so that that's exactly what's here, and so that's in the instantaneous stabilizer as well, and that can take, and ZB is there also, so we can take that to ZB, and you can keep going through the instantaneous stabilizers. So that's our construction. I guess I had a slide on this. Sorry, I should have. I'll let you stare at this for a little bit. But this is exactly what I was saying for the first 2 rounds, going from the first 2 rounds. And one thing to recognize is that we've really defined a generalized Bacon-Shor code here, where we have a set of checks on the lattice, but it's not a complete set of checks. The Bacon-Shor code between successive pairs of rounds will be different, but we have a Bacon-Shor pair Bacon-Shore code for each pair of successive rounds. Let's see. I think that's all I wanted to say there. Yeah, this carries through for, you can check the math for the other ones similar to what we did for that first pair. Now, what's the distance of the code? So the naive thought would be, well, and I had this naive thought, well, maybe we should just look at the distance of each of the instantaneous stabilizer groups, and that should be good enough, right? It's protecting information there. And so it's optimal if we place the defect in the center, because then the distance from the hole to the edge is only roughly d over 2, and it's a weight 2 check operators, so we have roughly distance d. And that really is the distance for the instantaneous stabilizer code at each round. But the problem is that that's not quite sufficient for preserving the logical information. And a better way of doing this is to look at those Bacon-Shore codes that are between each of the pairs of rounds and figure out what the distance is there. But it turns out that's not sufficient. And we got frustrated. We're like, we've come up with this construction, but we're having trouble figuring out what the distance is. We're not even sure exactly what all goes into that. So we just decided to put it out. And I think it was literally the day after we put out our paper, Fu and Gottesman put out a nice long paper on distances in Floquet codes, which we're still going through. I think I'm correct in saying that we didn't say anything wrong. I think we can use some of their terminology to be clearer. I think it's also correct, though maybe other people have looked at this more than I have, I think it's also correct to say that while they have provided some better upper bounds on the distance than we had in our paper, it's not completely clear yet how to really define the distances in a way that really tells you what the error correcting properties are here. So if any of you have looked at this more carefully, I'd love to pick your brain about it. Happy also to tell you what we know so far, and we're actively reading that, and we'll be revising our paper. As I said, not because I think we did anything incorrect, but just because I think we now have some language that people will be using, and that will make the discussion of distances clearer. We've defined a whole family of Floquet Bacon-Shore codes. You can put in lots of defects. We could have done put in 4 defects. I'm showing it for 9. I'll just point out that there's no point just putting in 3 because you might as well get unless there's some peculiar thing with distances that we don't understand. It looks like we might as well take advantage of the full symmetry there. So we have this nice family. I'm not sure what it's good for, but it does help us think further about how to design Floquet codes, and I hope that this will at least help spur people to have a broader view on how to think about Floquet codes, which are just really cool. Yeah, I've thought about error correction for a long time, and it had not occurred to me that by shifting around what you're meaning by your code space from round to round, that this would be an advantage. So I was very excited when I learned that idea. Yep. So there's lots more to be done. I have a couple more comments on just there's nice properties that some errors are just self-corrected by the measurement schedule. Decoding's a bit complicated because it's really a decoding hypergraph. And this doesn't possess a threshold, so we know there's a limit on how useful this would be. And then, there's still open questions as to when you can construct Floquet codes, what are barriers to constructing Floquet codes, what are good properties here. And as I said, I believe there's still open questions with respect to distance in Floquet codes that haven't been answered by the Fu and Gottesman paper. So that's everything on the second topic. I'm happy to take some clarification questions here. But I also was going to just do real brief glimpses of a few other topics in case we run out of conversation topics. So any questions on the Floquet code stuff, or should I go on to brief glimpses of other topics? Okay. So these slides are provided to me by Namit. Though some of them we work together on, some of them not. We have a coherent rank simulation approach, and I think this may be of interest to some of you. It has advantages and disadvantages. We can talk more about when there's an advantage or disadvantage. The paper came out last year, so it's been out for a little while, but not a huge long time. Yeah, we have. I think it's. There are a number of questions that are still open. On the other hand, we were excited to already see stellar representation come up earlier, et cetera. I just feel like somehow the three speakers so far have just gelled great. Another thing I just wanted to point out is a paper that has appeared on the arXiv, or maybe has appeared on the arXiv, because if you know the code, you can find it, but it hasn't appeared. So it's out this morning on a dual unitary shadow tomography approach. So Clifford is known to be optimal for certain settings, and what this paper shows, I wasn't on it, but what this paper shows is that there are settings in which this dual unitary, which have the strong operator entanglement aspect, does better. So talk to Namit if you're interested in hearing about that. The team has been looking a lot at qubits and qudits, and how are we pronouncing these, Namit? QNATs. Okay. And in some sense, those are just CV, but we're sort of emphasizing that it's in this family of where the D goes to infinity. I'm not going to go through this whole chart. Most of what's in the chart was known, but there are a few things where it says this work, which is in preparation. And the other thing is, I'll just comment that in some cases, it was really hard to find these results. And they may be sort of buried in the mathematical literature and not even in the quantum, normal quantum phrasing. And so we're working on a paper that outlines these things. So we do think, yeah, go ahead, Namit.
I just want to say that reference 25 is speakers.
Ah, cool.
You got it.
Thank you. And, sorry, I was thanking him. I have 2 more slides or 3 more slides, yeah, sorry. We also are looking at this in linear optics. Again, we have some things that we think are new results, but a lot of it was pulling things from the existing literature. Namit does a lot on scrambling in quantum many-body systems. There's lots of applications to this to verifying quantum hardware, interesting phenomena in quantum mechanics, and also maybe hard to reverse, and so might make a Wigner friend experiment that's compelling. And I'll just finish with a historical perspective, which was that back in 1972, the director at NASA Ames brought the first massively parallel computer to Ames. And sometimes I ask people to guess what the power of this computer was, but it's on the slide. So it had a 50 megaflop peak, okay? And when I first got to NASA And some of the people in the supercomputing system had access to some quantum hardware, and they were like, what is this crap? This doesn't do anything. It's supposed to be better than our supercomputers, et cetera. And I'm like, don't worry, it's just a physics experiment. We're getting to something longer term, but it's just a physics experiment at the moment. And then some of the older folks came by, and they said, we know what you're going through. We had to show people that we could do fluid dynamics and turbulence and things like that. And this would replace some of what was being done on wind tunnels back with this 50 megaflop peak computer. And so if we can have even a small fraction of the impact that parallel computing has had on the world, I think we'll make a significant impact. Thank you.
Thanks very much, Eleanor, for a fantastic talk on several topics. So I'm taking questions now, I presume, on the whole thing. Questions? Yeah.
Maybe I have sort of a conceptual question on the first part. So it seemed to me like there's maybe two hard issues that you're trying to get at, and I was wondering if you could try to disentangle them a little more for me. So one seems like an intrinsically sort of classically hard problem already of, like I have a person who may be making effectively deterministic decisions, but there's somehow like random environmental variables, and so there's some chaotic dynamics that maybe generates the message. And I mean, I guess I'm trying to wonder if already that kind of, does quantum give something fundamentally beyond that that would make this reversibility experiment somehow steep?
Yeah, so maybe I didn't, I probably didn't emphasize this enough. So all we're asking the human level artificial intelligence to do, and this is actually a little bit of an additional assumption, is that we want quality to make a measurement of a qubit and think about it and compose a message and send it off to Alice. And the reason why that's important is that we need to have this entangled state for the extended Wigner friend scenario. And then what we want to be able to do is to have either Quali measure it or Alice reverse everything and make her own measurements. And then we can get statistics out of what quantum theory predicts. And so there's no way to do that part just classically. That might not have answered your question.
Yeah, I guess somehow maybe so maybe if I can ask it a slightly different way then, is there sort of something important about taking maybe the like intelligent limit of having like quality versus just some like few qubit system where I try to entangle with one additional bit and then do something based on the outcome of it?
Yeah, I mean it really depends what your comfort level is. It's really trying to get at making it hard for people to be happy.
Dropping 3 and 4 on this list.
You're happy dropping 3 and 4. Okay, so you're happy to have your thoughts aren't real. Yeah. Okay. Yep. That's fine. Okay. Yeah. So we're trying to make it hard to drop 4. And by the way, you can drop 3 and keep 4. So it's actually, if your thoughts aren't absolutely real, then it's even easier to keep 4. So the reason we're pushing on the human level artificial intelligence is to make it hard to give this up. But let me emphasize that we give compelling arguments for all of these in the paper. And it has been misunderstood by a few people saying that we are claiming that all of these are reasonable, right? But the whole point of the theorem is that we're going to have to give one of them up. And we were trying to make it seem, like it's just not obvious. It isn't obvious to us, I think, what's the right one to give up. I don't really want to give up friendliness. Now, maybe you are totally happy with that, but that's, and that's totally fine.
I'm scared about breaking relativity.
Yeah, fair enough.
So 1 and 2 seems.
Seems, yeah.
Yeah, Steve.
So one of the assumptions you made, which is not in this list, is that idea that the measurements can be reversed. And I mean, there's certainly a strong view within a subset of people doing quantum mechanics is that measurements are a different process that is fundamentally irreversible. So where does that come into the trend of logic?
Yeah, so we tried to avoid saying measurement because it carries, for some people, this, well, then it's just not reversible, and then we can't do this definitely because you have to be able to reverse. So what we were saying was observation. That might go into the same directions, but the idea was you have this artificial intelligence running on a quantum computer, and it can interact with a qubit in a way that generates thought processes like a human would see if they interacted with an experimental system. It's like what a human, it's only like what a human is experiencing to the extent that the human-level artificial intelligence is running something like what's going on in our brain. It might look very different, but that somehow the artificial intelligence is interacting with the system in a way that it could report on it. And then we're playing with that by, it has reported on it, and then Alice has a choice as to whether to open the report or send it back so that the whole process could be reversed. And you're totally right. I mean, you cannot do this if we just rule out being able to reverse. But the Wigner-Friend paradox is really trying to push on when is a measurement really happening and how should we be modeling the system. And so I think it at least pushes people on, okay, well, what do we mean by interacting with that system? When would we call that totally irreversible or not? Did that help?
Yeah.
Okay.
I think, oh, here's a question.
I have a question on the second part of your talk. So can you comment more on how you do logical operations under inequalities? I mean, to keep the weights with other
Yeah, I mean, we have not written those out carefully, so I don't know how complicated that is, but at the moment you can look at it as a memory. I don't think it's hard to do this, but actually I should check maybe, so I wrote it down and I don't remember, but that wasn't the emphasis of the work initially, but it's a perfectly reasonable question. Yeah.
I also have a comment. So your work reminds me of a paper by Google Compton. The paper is called Less Equal, More Fractal. So they concatenate the protocol with the self to get a larger instance of it with fewer interactions. So I think the idea behind most papers is that with taking some of the base from the different protocol, you can actually get better performance, whether it's higher fidelity or more longitude. And this is pretty cool.
Yeah, and we have some hope that by combining them you could get something even more powerful, but it may just be that you're going in one direction for one of them and one direction for the other, but yeah.
Thinking about that, and then I was asking, the motivation behind the first question was like, how do you do adversary review with like, the version of the
Yeah, fair enough. Yeah.
Right, okay, I'll take one very quick question. We need to move on.
It might be related to the previous question, but for this, when you say that Cody did some measurement and send it to Alice, and then Alice has a choice whether to open it. Then the measurement has been done, like something has been communicated to Alice. The choice is there whether she opens it or not, then you destroy all the coherences. Right? It's just a stochastic mixture of two states then.
Well, it depends how you're communicating it. And
Any form of communication means that I destroyed the coherences. I did some measurement on the system, got some classical result, and that is.
no, we're not assuming you got a classical result.
Then how do you communicate to Alice?
You'd send qubits. Yep.
Let's thank Eleanor for a fantastic talk.